So last time we left off our lecture talking about sequences. So just to recap quickly, given a metric space M, when we say that xn is a sequence in M, we mean that xn is in the list x1, x2, x3, x4, x5, so on and so forth, of elements of M. Now, a little bit of a notational sort of convention, just to simplify things, is when we say xn, we could be referring to the whole sequence. Or we could just be referring to like the nth element in the sequence. Normally I'll change the letter in order to say we're talking about the nth element in the sequence. Right? I'll say like xi or xj or xm or something like that. Okay? So that's a little bit of a source of ambiguity, but it should be clear from context whether you're talking about the entire sequence or just a particular element of that sequence. All right. Definition. In a metric space M, we say that a sequence xn converges to a limit L when, for any real number R, a positive real number R, there is an n, such that when m is bigger than n, so here we're talking xm is a particular element of the sequence, for every m that's bigger than capital N, xn, the distance from xn to L is less than R. In other words, as we go on in the sequence eventually enters the ball of radius R around L and stays inside there. All right, so the sequence is hopping around. It could go inside the ball, come out, go inside the ball and come out, but eventually goes inside that ball and stays there. So, like, what does it mean to not converge? To not converge, right, how do we negate this statement? Look at this statement. So this statement, how is it quantified? For every R, there exists N. So the negation of that is what? When you say for every R, there exists N, the negation is what? The negation of for every R, there exists N, something, something. For some R, there is no N, right? For some R, so when you want to negate that sort of thing, for some R and every N, the statement is negated. For every R, there is no N. Or for every, there is an R for no N. There is an R, you said it better than I did. For some R, there is no N. Great. That's exactly right. For some R, there is no N. Or for some R and every N, whatever you want to be true isn't true. All right. So what does it mean to not converge? To not converge, for xn to not converge to L, there is an R such that xn doesn't enter the ball and stay inside the ball. So no N will work. There is an R such that xn doesn't stay inside. It could enter. Doesn't stay inside BRL. It always hops out, even if it goes in. It goes in, but it hops out. So, for example, this sequence here. Well, -1, 1, -1, 1, -1, 1, -1, 1, -1, 1. That doesn't converge to anything. In particular, it doesn't converge to -1 or 1. For example, okay, -1 to the n does not converge to 1. Why? Take an r equal to a half. Anything smaller than that will work as well. Take r equal to half. Look at that ball of radius 1/2 around 1. The sequence never goes inside that ball and stays. It does go inside it. It keeps going inside it, and that's fine. Okay, but it never stays inside there. Convergence means you go in there and you stay inside there. If it keeps going inside there, you know that there may be this subsequence that converges, but I don't want to talk about that. That's a bit much for where we're at. So, for example, the sequence 1 over 10 to the n, that converges to 0. Right, back in calculus, you say, well, 10 to the n goes to infinity, so 1 over infinity is 0. Okay, that's fine from an intuitive perspective, but it's not rigorous, what you're saying. Here's a rigorous proof. Let r be bigger than 0. Okay, let r be a positive number. You don't know what it is, but it's small. So r is some really small number. How small? Really small. So small that it makes no sense in a physical universe. Okay, it makes no sense in a physical universe. This r, it's so darn small. Okay, in the decimal expansion of r, there is a first digit that is non-zero, right? That is, r is equal to 0 point digit 1, digit 2, digit 3, digit 4, digit 5, and those digits are all 0 until you get to the nth digit. And that nth digit is non-zero. Has to be, because r itself isn't 0. So, say that d1 to dn minus 1, they're all 0, but dn is non-zero. It's the first non-zero one. Okay, now, for any m that is bigger than or equal to n plus 1, 1 over 10 to the m is less than r because it has digit 1 through digit n equal to 0. Therefore what? Therefore, 1 over 10 to the m, absolute value, minus 0 is less than r. This just becomes that. But that's the distance metric, the distance function in the metric space. And that's less than r, as required. Okay, another example. Okay, in your homework, so let's talk a little bit about this homework problem here. M1 is a metric space with distance function d1. M2 is a metric space with distance function d2. Define a distance function on M1 cross M2 by the distance from x1, x2 to y1, y2 is just distance 1 of x1 to y1 plus distance 2 from x2 to y2. That is a metric space. You will prove that it is a metric space, but it is. And we'll just assume that for the time being. Okay, so in homework problem number 1, given metric spaces M1 and M2 with distance functions D1 and D2. Okay, M1 cross M2 with distance function D1 plus D2 is again a metric space. Okay? So in problem number 1, you will prove given metric spaces M1 and M2, distance functions D1 and D2, M1 cross M2 with distance function D1 plus D2 is again a metric space. By the way, these Cartesian product type problems, so as I was saying before, one of the main stumbling blocks in the upper level courses in the math major modern algebra and real variables, particularly in modern algebra. Functions are a stumbling block for students. Functions give them problems. So I tried to emphasize the functions with you guys. I think you're doing good, a lot of you, with that. Another one that's a stumbling block is Cartesian products. Right? You have two objects of a special sort. So now I'm going to speak in disgusting generality. You have two objects, both of the same sort. So I have two phlebes. I have A as a phlebe and B as a phlebe. And then you take A cross B and you get another phlebe by using the fact that A and B are phlebes, whatever phlebe means. Right? This is a stumbling block for many students. Okay, this construction. Right? I got widget A, widget B, and I take the Cartesian product of A and B, and I make a widget out of the Cartesian product by using the fact that A and B are widgets. All right, so that's what we're doing here. We got metric space M1 and M2, distance function D1 and D2, which makes M1 and M2 metric spaces. Now I'm going to take the Cartesian product, and that's again going to be a metric space. Okay, so given AN sequence AN converging to L in M1 and sequence Bn converging to, no, I can't use AN converging to L and Bn converging to K in M2 show that the sequence A and Bn converges to Lk in M1 cross M2. So I have a sequence AN going to L and a sequence Bn going to K in metric spaces M1 and M2. So I have this sequence AN Bn in M1 cross M2. I want to show it goes to Lk, converges to Lk. All right? All right, so how does one show that sequences converge? Let's go back to the definition. What's the first thing in a convergence proof? For any real number r, there is an n such that something happens. For every r, there is an n. So what do I have to do to prove something for every r? What did we do last time? So I want to prove something is true for every real number r bigger than 0. And, thinking of r as something tiny typically. What's the first sentence? Can you watch Jeopardy, anybody? Anybody watch Jeopardy? Oh, sorry. What is the first sentence of proof of convergence? Where the definition of convergence is this. For every real number r bigger than 0, there is an n that does something. For every r, there is an n. So what do I have to do in the proof for convergence? Well, what did we do last time? What did we do last time? Are you hearing me, you guys? What did we do last time? when we're proving something converged. Let R be bigger than 0. And you start with that. You have to prove something is true for every R. You have to prove something is true for every positive number R. So start with some positive number R. You can't say what it is, just it's very small. Okay, so let R be greater than 0. Because AN converges to L in M1, what happens? Because AN converges to L, so we're not proving AN converges to L. We know AN converges to L. All right, that's a given. Given that AN converges to L and BN converges to K, show that this pair, AN-BN, converges to LK. Okay, this we don't know. This we do know. This we do know. This we don't know. So we can use the properties of these to prove that this has the right properties. Okay. Because AN converges to L in M1, what happens? What must there be? For every R bigger than 0, there is N1 such that when M is bigger than N1, the distance from AM to L is less than R. Okay, but the R won't quite do it. The R won't quite do it. What I want to use instead of R is R over 2. Is that still positive? Is it still positive? Yeah, of course it is. Right? So why don't we write that down? I didn't say it. Why don't we just say it here? Oh my goodness. Okay, note that R over 2 is bigger than 0 still. Because BN converges to L in M2, there is what? What must there be? What must there be? There is N2 such that when M is bigger than N2, the distance of BM to L is less than R over 2 again. Are N1 and N2 the same? Must N1 and N2 be the same? Of course not. They need not be. If they need not be, right, you can't assume that they are. If it might be that they are, and that causes a problem, then you have to deal with it. It doesn't cause a problem here. So we don't really have to think about that. All right. So now let n be equal to the larger of n1 and n2. Right? I mean, either the same or different. One of them's the biggest. Right? Well, one of them's the biggest, or they're the same. The same. Doesn't matter. Okay? Just let n be the larger than each of them. At least as big as both. So, when m is bigger than n, bigger than or equal to, whatever. Bigger than or equal to doesn't quite matter here. So when m is bigger than or equal to n, what happens as far as these two inequalities go? Which one happens? If m is bigger than n, is this true? If m is bigger than capital N, right, which means m is bigger than n1 and m is bigger than n2. Right? So when m is bigger than n, which means m is bigger than n1, and m is bigger than n2, we get that the distance of am to L is less than r over 2, and the distance 1, I didn't use the distance 1 and distance 2, did I? Distance 1, distance 2, and the distance 2 of AM or BM to L is less than R over 2 as well, both of them. Therefore, the distance of the AM, BM to, oh, it wasn't L, I'm sorry, it was K. BM converges to K, not L. This one was L, and this one converged to K. BN converges to K. Ugh. BM converges to K. Because BM converges to K, right, the distance 2 from BM to K is less than R over 2. All right. So therefore, the distance of AMBM to LK is equal to what? Well, what's it equal to by definition? By definition, it's what? How did we define it? It's the distance of AM to L plus the distance of BM to K, which are both less than R over 2. So this is less than R over 2 plus R over 2, which is equal to R. So are we done? When M is bigger than capital N, the distance in M1, M2 of AMBM to LK is less than R. So are we done? Is that what we needed to show? For every R, there is an N. For when M is bigger than N, the distance of the sequence to the limit is less than R. That's it. So this is done. As required, or whatever sort of fancy things you might want to add in there. As required, meaning there was some requirement that needed to be proven, and we did that. Okay? All right. What else might we say about sequences? Let's prove the following. So suppose that well, let M be a metric space. And say that that L and L be an element of M. So if BRL contains an element, if for every R R bigger than 0, BRL contains an element X not equal to L, then there is some sequence Xn in M converging to right, there is some sequence Xn such that Xn converges to L. Proof? Right, consider the balls of radius 1 around L, the ball of radius 1/2 around L, the ball of radius 1/3 around L, the ball of radius 1/4 around L, etc., etc., etc. So, by assumption, let X in, say Xi, be an element of B1 over I. Well, the I looks bad there, doesn't it? Let Xm be an element of B1 over M L with Xm not equal to L. Oh, there's a sequence Xn in M such that Xn converges to L and Xm is not equal to L for all M. Sorry. You always have a sequence which converges to L. That would be the sequence L, 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 L. Right? So let Xm be an element of the ball of radius 1 over M around L with Xm not equal to L. So now we have the sequence x1, x2, x3, of elements x1, x2, x3, so on and so forth. Okay, where none of them okay, let's show that xm converges to L. I mean, we've just created this sequence. Now let's show that it converges to L. And as an assumption, that 1 over n converges to L. I mean, we know it does, but let's just assume it. I mean, we haven't proven that it does, but I mean, let's just assume it does. Okay, let's assume that 1 over n converges to L. It's a reasonable assumption. Or converges to L, converges to 0. Let's assume that 1 over n converges to 0. Well, since 1 over n converges to 0, right, there is capital N such that for every m bigger than n, 1 over n is less than r for any real number r bigger than 0, or 1 over m. 1 over m is less than r for any real number r bigger than 0. So that's because 1 over n does converge to 0 in the real numbers. Okay, so now consider the element of the sequence xm. Because xm is an element of the ball 1 over m around L, the distance of xm to L is less than 1 over m. So as long as, right, and we are therefore guaranteed that the distance from xm to L is less than r because 1 over m is less than r. So that's exactly it right there. For any real number r bigger than 0, there is this m bigger than or equal to n such that, okay, when m is bigger than or equal to n, xm, its distance from L, is less than r. We can say it a little bit better. Let me say it. Let me get another go at it. I don't like the way I said it here. There's a better way to say this. Kind of going in circles a little bit. Let us show that xm converges to L. Okay, so let r be greater than 0. Okay, and let n be some number greater than 1 over r. And, again, the idea is that r is really small. So when I take its reciprocal, 1 over r, it's something big. But at any rate, let n be an integer that's bigger than that. Right? let n be some integer such that n is greater than 1 over r. So now, if m is bigger than or equal to n, then the distance from xm to L, which is less than 1 over m, and this is because xm is an element of the ball of radius 1 over m around L. So its distance from L is 1 over m, right? And then because m is bigger than or equal to n, right, when I take the reciprocals, right, when I take the reciprocals, the order gets flipped around. But 1 over n is less than r, and that's because n is greater than 1 over r. So when you take the reciprocal, the order gets flipped around, as required. So for every r bigger than 0, there is this n, it's just some integer that's bigger than 1 over r, such that for every m bigger than n, the distance from xm to L is less than r. Well, the distance of xm to L is less than 1 over m, because xm is in this ball, so that's just the definition, right? Which is less than or equal to 1 over n, because m is bigger than or equal to n, which is less than r, because n is bigger than 1 over r. And remember, when you take reciprocals of positive numbers, in an inequality, the inequality gets flipped around. Okay, so that's another just sort of interesting fact about sequences. Okay, final topic, called continuity, which of course is something you've been talking about in Calculus 1, Calculus 2, and Calc 3, but again, it's something that's not really ever defined in a rigorous fashion. 100 years ago and a generation ago, it kind of started dying out when I was in college. We still purported to be teaching continuity in calculus, but not really. I mean, we talked about it, but I mean, it's just not something that that really you can do in calculus. It requires more thought, more time and more thought. Not that you can't do it. I mean, you could, but you have too many other things you need to cover in calculus. All right, so continuity. Consider metric spaces m and n, okay, with distance functions let's call it dm and d sub n, like that. Okay, now consider a function f from m to n. Okay, recall the definition of preimage. Right, if A is a subset of the range n, if A is a subset of a range n, then the preimage of A is equal to the set of all x in M such that f of x is in A. Right, that's the preimage of A. And the definition is as follows. So the function f from m to n is said to be continuous when for every open set O in N, for every open subset O in N, the preimage of O is an open subset of M. So preimage of open sets are open. That's the rigorous definition of continuity. Okay, in this metric space terminology. It is one of these definitions, if you ever saw the formal definition of a limit for functions on the real numbers, for every r bigger than 0, there exists a delta bigger than 0, such that, you know, some various things. For every epsilon bigger than 0, there's a delta bigger than 0, satisfying something. Okay, but if you kind of want to boil it down to more succinct language, it's this. Okay, for every open set in N, the preimage of that open set is open. That's what continuous function is. For every open set. Now, you could talk about continuity at a given point, but, you know, I mean, we'll just talk about just global continuity here. So what about the homework? So we'll talk more about it next time, but let's take a look at that homework problem dealing with continuity. So let M, N, and P be metric spaces. F from M to N and G from N to P are continuous functions. Okay, so M, N, and P are metric spaces. F from M to N and G from N to P are continuous. Show that G following F from M to P is continuous. The composition of continuous functions is continuous. Okay, so you have to show that every open subset of P, the preimage under GF of an open subset in P is an open subset of M. Okay? But you can use the fact that the preimage of an open set under G, the preimage under G of an open set in P is an open set in N. Well, since the preimage of that open set in N under F has got to be open in M, well, you know, that's mostly it right there. It's mostly it. It's not quite everything. It's not quite everything. But we'll talk more about that tomorrow. So right now, let's do another observation on continuous functions. Theorem. Say that f from M to N is continuous, and xn converges to L in M. Show that. I'm saying it as an exercise, sorry. I should say it as an if-then. If the function f from M to N is continuous and sequence xn converges to L, then the sequence fxn converges to fl in N. So you have a convergent sequence in M and a continuous function f. So then when you take the image of that sequence, so you have sequence x1, x2, x3, x4. So you can hit it with f. So I got fx1, fx2, fx3, fx4. It still converges to L. Okay? So, how can we prove this is the case? Okay, let R be bigger than 0. Okay, let R be bigger than 0. All right, and consider the ball of radius r, around f of L in N. One of the homework problems is that the ball of radius r around an element x in a metric space is an open subset. Okay, so homework problem number 3 is that this is an open subset. BRFL is an open subset of N. Because F is continuous, right, what can we say about the preimage of this? What can we say about the preimage of this open subset of N? Because F is continuous. The preimage of an open set is open. The preimage of the open set is open for continuous functions. That's the definition. Because F is continuous, this is an open subset of M. Because FL is in BRL, so furthermore, this open subset because, well, f of L itself is an element of BRFL, right? The element L itself, L is an element of this open subset, preimage BRFL. Because FL is an element of that ball, BRFL, its preimage has to contain that element L itself. Now, because the sequence because this is open, for any r bigger than 0, because this is open, there is some r such that the ball of radius r around L in M is a subset. I shouldn't use the same r. There is some s such that the ball of radius s around L in M is a subset of this. So now the image of this ball of radius s around L is inside of the ball of radius r around f of L. because the sequence converges, because xn converges to L, because xn converges to L, there is m such that for m bigger than or equal to n, xm is always an element of the ball of radius s around L. Therefore, f of x m is an element of f of the ball of radius s around L, which is a subset of the ball of radius r around f of L. So that's what we wanted to show. For every r bigger than 0, there exists an m, or capital N, such that for m bigger than capital N, fxm is in the ball of radius r around fxl. In other words, the distance from fxm to xl, fl, is less than r. Okay, so that's the final thing we needed to show. Try this one for next time. So for next time, try the following. The converse of that, if for every xn that converges to L, we have that fxn converges to fl, so this is in n, or in m, if for every xn that converges to L in m, we have that fxn converges to fl in n, then prove that f must be continuous. So this is a converse to that statement that we just proved. We proved when f is continuous and xn converges to L, then fxn converges to fl. Now, if you have that convergent sequences go to convergent sequences, the image of a convergent sequence is a convergent sequence whose limit is the image of the limit before, then f must be continuous as well. It's an if and only if statement, and that's an interesting exercise. So give that a shot for next time. Maybe we'll cover it as well. Okay, so that's all for today, and that's all the material for the course. So next